Myself, Stefano, and Bruce, we're going to talk about device trees. We'll get the coordinates at the end here, but there will be a meeting about this. So if you have questions, there will lots of time to really go into the depth of this stuff. What I'm going to talk about now is kind of what we are prototyping. This is not by any means that this is how it's going to be, but it's so much better if you have a prototype and you have something that works, then you have something to discuss and make sure that it fits for all the various use cases that we're thinking of. So let's get started here a little bit. So this is actually our previous generation SoC from Xilinx, just as an example. As you can see, there are lots of stuff running here, and there's a lot of things that needs to be configured. Lots of processor, lots of software that needs to know where the heck are these things. Things like addresses, how much memory do I have, topologies, clock topologies, bus topologies, all these different things. In this particular one, we have a few R5s running here. We have a few A53s running here. We have this weird thing called FPGA, where you can have a bunch of soft cores, so other processors running here, and so on and so forth, right? And there's a lot of this kind of information that needs to go to the software. And also it comes from different personas. So some things come from the guy who designed the hardware, right? This address, this register is at this address, and so on. So some things can be configured when you put this thing on a board, that you're only using the CAN pinouts, for example, and not some other things. Other things come from more of a system architect that want to say that, all right, I want whatever RTOS running on the R5 should have access to the Ethernet, but I want someone else to have access to something else. So when you think about this, you have to think about where the information comes from, because otherwise you can't have hardware guys, software guys, everyone sitting in each other's lap and hope that will work, right? Also, the configuration happens at different time. So it could be during compile time or link time. It could be during boot time, or with overlays, as we talked about before, it could be during runtime as well. So you have to think about the various flows depending on when you're going to use it as well. And it's not just the RTOS and the Linux, for example. As you can see here, you have all these different operating environments. I'm calling it that for lack of a better term. Move over here. So you have things like various firmwares. Before that, you might have uboot and things like that. You have hypervisors. This is sort of the worst case scenario. Not often that people have all these things running at the same time. But you can have a trusted environment with applications here, hypervisor with Linux, RTOSes, maybe other RTOSes running here, or bare metal, or microblaze, that's our soft core in the fabric or the FPGA. So all these environments need this kind of information, right? So it's not, don't think about it just as an OS thing. It's really the whole environment needs to get a bunch of information for the software to be configured. And you really don't want to go in and change the .h file over here, change the device tree over here, change the line of code over there, right? You want everything to come from one source, basically. All right. So the problem statement is that this is really difficult, and it's very ad hoc these days. And when you think about things like we do in OpenAMP, which is this way of talking between different partitions, then you have to set up shared memory. All right. If you do something wrong there, you can debug that for weeks. So we really need some industry standards, common tools, and so on and so forth, right? And also verification is really critical. Again, you can debug these things forever and ever. So it's not just to get the information from one source, sort of trickle through various personas, but you have to be able to verify at the end that, all right, this RTOS image that I got has the same view of the hardware as this other partition, right? Maybe you get out of timings otherwise here. So device trees, so actually at Xilinx, we had kind of a system like this. Internally, we had our own XML files. It wasn't really that well specified, and it kind of changed from one release to another. And as we are trying to work on decoupling all our different tools, we have tools for the hardware guys creating stuff into the FPGA, and our system software and so on, we started to think about this problem. And we probably have a worse problem than most people, since we have this hardware that can just change under you by loading a new bit stream into the FPGA. So we said it doesn't make sense for us to continue with this proprietary way of doing it, because there's no way we can get the RTOS guys, for example, to adopt to it, and other people, right? So we started to think about, look out there, and device trees was an obvious choice, but device tree has this property that it's really only looking at one address space. So if you have something else running, some Cortex R5s, for example, that have a different view of memory, you can't really express that in a traditional device tree. So we started to think about it, and really saw that there are two things that you need to add to a device tree to be able to solve these problems that we're talking about. The first one is more of a specification. You have to be able to specify multiple CPU clusters or multiple masters. It could be something else that is accessing the memory and the devices and the nodes and so on. So that's more of a specification task. We need to change the device.org specification. And I'm going to get back to this. That doesn't mean that every Linux has to change. We want to do this in a way so that no existing software has to change at all. Really want to emphasize that. That's a really key point. So that's one part. How do we specify all these things? The next one is, how do we then allocate resources to these different domains? So we came up with the name domain for the different partitions, if you will. Might be because Stefano has been working on this, and he's the Zen maintainer, and the virtual machines are called domains there. So, but it's a really good way of looking at it, right? And by the way, one of the intent here is to align this so that the hypervisor, Zen in this case, but also talking to other hypervisor vendors using the same format here, just like we do for AMP and for the other operating systems. So far in our prototype, we are putting all this configuration information in the chosen node, and Stefano will go over that a little bit later here. Very briefly, on Thursday, we will have a chance to look at this much more in detail. So this is sort of a diagram from hell. Not going to go through all the various details here, but the main point is that you have these different personas. So here you have a bunch of different hardware personas. For software guys, it's only the hardware guys. But they're actually very different. You have the ones doing the board are very different from someone who's creating something in the FPGA, for example, and the guy that originally did the SoC. Right? So you have these different kinds of information. You want to decouple that, so when you do a new board, you shouldn't have to go in and edit in all the other files. So you should really make sure that the board-specific stuff gets from a separate source. Then we have something we call a system architect. That's the guy saying, oh, I have all this hardware to play around with. Well, how much should I give to the Linux guys, and how much can I give to the FreeRTOS guys or the VxWorks guys, and so on, or which devices should go where, and so on. So that information is also in the device tree format. So all these different things are in a device tree format. For us, you could just put them together into one file, but again, to be able to separate the different personas and so on, what we are doing is that we're keeping them as separate files. Here we have then two different flows. Obviously, you can have multiple of these, but let's look at Linux first. So we are prototyping this program called Lopper. It's a tool that Bruce is working on, and he will talk briefly about that in a few minutes. When you run this Lopper tool that's built on top of DTC and libftt and things like that, then you specify basically a domain, which is one of these address spaces, if you will, and then it will go in and prune the tree. So Lopper is actually one of those tools, if you do gardening, you chop the tree, right? So it's pruning the tree here, really, throwing away all the stuff that doesn't apply to this particular domain. And out of that, you get a traditional, quote-unquote, device tree. It actually has a bunch of other transformations that you can put in. It's a pluggable architecture, so you can put in stuff, so that the idea is that this should look exactly like the device trees that you had before. Maybe one day in the future, we do want to have Linux to be able to read system device trees so that it can be the master in starting up other things. but that's for later. We're thinking about to make sure that that's possible, but let's not boil the ocean in one go here. Here we have sort of a typical RTOS flow. It will look different for different. Some RTOSes are smart enough to actually, just like Linux, dynamically read a DTB file. Others, like Zephyr, you go through some conversion. First, you create a regular device tree out of this, but then you go some conversion to create whatever config.h and config.c and all the pound defines and all that good stuff that you need there. And then as an output here, typically you get like a Linux kernel image. Obviously you have the device tree here because that needs to go to on the board. In the RTOS, you typically get an ELF file, but we also keep the device tree here so that we can do some verification. Because it could be that these guys are out of sync. Can someone change how much memory that this guy should go? You don't want to load an old release of this and then suddenly grab too much memory. So you want to be able to, at the integration or runtime, be able to verify that this guy's view of the world and this guy's view of the world are compatible. We have a bit of material here, so I'm going a little bit quickly here. Here's another use case. This is similar here, but this is for a hypervisor, SAN in this case. So SAN would get more stuff because it's interesting of bigger part of the world, multiple domains. And then what we're looking at in the future to have Zen read, right? Today, Zen is reading a device tree, but it's really more or less the same as the DOM0 device tree, and then you have some marking of what's not supposed to be viewed by DOM0, if I understand it correctly. But here we want to make sure that you can describe to Zen exactly what the different domains are allowed to use and so on. Another use case is QEMU, the simulator. In the Xilinx version of QEMU, we actually today have something that's a little bit similar to the device tree, but it was done quite a long time ago. You feed that into the QEMU, and then QEMU knows what kind of hardware to simulate, right? Upstream QEMU is a little bit different. Actually, you kind of compile those things in, and then you can generate a device tree to be used by someone else. We're trying to upstream this, and it's available for anyone who wants to see it. But we do want to make sure that we're using the same kind of format for these two. Okay, I'm doing good here on time. So with that, I want to present Stefano, who's going to talk a little bit about the format. And again, this is just the proposed format, what we are using right now in our prototypes.
Yeah, I'm going to show you for just a couple of minutes a little teaser of the spec. Let's see if it works. Yes. So these are some of the spec changes that we are looking at. So let's start with this. So we have multiple CPUs node. As you know, there is only one CPUs node today. So we are going to have multiple, one for each CPU cluster, one for the F53s, one for the R5, and other heterogeneous clusters. They are compatible CPU clusters. This is new. What also is new is this ranges map property, because different CPU cluster can have a different address map. Like a specific device, MMIO region could be mapped at different addresses. And we have one example of this on our Xilinx boards, where there is a little area of memory called TCM that shows up at different addresses at the A53 cluster and at the R5 cluster. Now, this is very similar to the ranges property for buses. So if you are familiar with that, it's almost identical. And the point is, if I go below, this is the R5 cluster, the TCM bus is mapped at 2 addresses, while before it was only mapped at 1 address, because in fact it was only mapped at 1 address of one of the clusters. Now note that this is not a configuration, this is about hardware wiring, so nothing that can be done about it. So this is a set of changes that we need to the spec so that we are able just to describe what is there. So that would be the first group that Thomas mentioned. Now, the second group of changes is quite interesting, because if I go under chosen, we're going to find a bunch of things, and these are software configuration issue, for software configuration properties. So this can be changed in software firmware. It is not about hardware description. There is a number of things that we are showing here under this open up domain node that we're trying to introduce, but I'll just highlight a couple. I'm not going to go line by line. We can go line by line on Thursday morning at 9 a.m., especially if you're interested and you have questions, shows up. But one thing is there is an access property that tells what resources this domain is supposed to access directly. In many SoCs, there are even hardware ways to enforce that a specific domain, like the R5, can only access, let's say, the Ethernet card, but they cannot access the SATA controller, okay? So there is a way to do that on Xilinx board, and I know that other vendors have similar tech as well on their SoC. So with this access property, you can specify which devices or memory region are directly accessible. So this is a memory region specified under reserved memory. This is, well, the TCM bus as before. These two are other specific memory regions that are used for communication with the FE63s. Like Thomas was saying, part of the difficulty of configuring OpenAMP is to be able to specify the shared memory for communication with the FE63s. So this is another one of those things that will go here under the access property. And that's another little special memory regions that are used for communication. You can also note that we have a flag that's passed together with what the domain can access that can have device-specific information, specific about the mapping, and that can be vendor-specific, for example. So the other thing that is interesting is here we are specifying on which CPUs this domain is relevant to. So here we are saying it's supposed to run on the R5 cluster. No surprise, this is the R5 configuration of the domain configuration. This is to say on which CPU specifically it is running on. So on our board, at least, the R5 can run in lockstep or independently. So this is saying I'm only running on CPU 1, not CPU 0. And there are flags that are specific to the architecture because there are some properties that are available on the R5, not on the FE63s, or vice versa, like lockstep. So here is the FE63 cluster, and as you can see, it's very similar. It's saying I'm running on the FE63 cluster, I'm running on all 4 CPUs, I'm running a TL2, and I can access this set of devices and resources. Many of them are the same you saw before because they are to communicate with the R5, so in this example, they're mirrored. And finally, the last thing I want to show you is the VM configuration. Like, as Thomas mentioned, we are trying to make this work not just for an OpenAMP setting, so native bare metal R5 or FE63s or things like that, but also for hypervisor. And as you can see, the problems are actually very similar. So we have to specify on which CPU is going to run, on how many virtual CPUs, this is obviously VM specific, and what resources is going to be able to access directly, and like memory, but also devices. So it's a very similar set of issues that we are trying to specify with exactly the same kind of node. So we should be able to have a single spec for both VM and physical. Now the part of the hypervisor is a bit greener than the OpenAMP side, so there are still a few questions still remain open, but it does include all that's necessary to create like a Xen DOM zero-less VM, which would be one of those VMs that start directly at boot from the Xen hypervisor. The last thing I want to show you, just in case to make these references a bit more clear, in case of devices, they're just pointing to a device, and in case of memory, they're just pointing to a specific reserved memory region. So if you are familiar with reserved memory, in reserved memory you specify a number of regions that can be assigned for one specific purpose, to Linux, for instance. And this is exactly what we are doing here. So we are carving out memory regions, reserved memory regions, and then assigning them directly to either one cluster or the other cluster, or maybe a virtual machine. So this is like a quick overview of the changes that we're looking at. And as you can see, they're clearly divided into the group for configuration, software configuration under chosen and reserved memory, and the others that are actually generic device tree specification changes.
And so obviously this input then, so this is what we just saw, the system device tree. We also saw the domain information under the chosen node here. And then you run this program Lopper that now Bruce will get into. And here you create a regular device tree where you see the regular CPUs group and so on. So maybe just quickly, if you can go over your...
I'm just going to go really, really quickly over this because a slide of a proof of concept tool is not all that interesting. We can do demos and show it in more detail on Thursday or whatever. But just to go along with the workflows that Thomas was talking about and the new bindings and the stuff that Stefano was talking about, have actually implemented a tool so we can have something to show that it's viable and that we can write things. So the only thing to know about Lopper is it's sort of, it takes all of these different inputs. Everything right now is sort of a device tree format. It can be anything. We'll probably do different front ends for it eventually. It's written in Python 3. The tool itself is pretty stupid. It's data driven. It doesn't have any intelligence, and it has the ability to call out to different loaded modules to do either processing of the nodes. If you don't want it to be completely data driven, you can do things in Python, and the same thing for backend. So we can do a single run of Lopper and output multiple device trees and call different backends to do code or device trees or DTBs or whatever we want. So, and of course it doesn't care. It can be a feedback loop where the output of one run of this can be fed into the next run, and you can keep going from there. And that matches up with the personas that Thomas was talking about, where different people can provide different chunks of inputs to this through the flows. Is it a minute or less? It's not bad.
Wow, we made it. There was too much information. So I guess we have a few minutes for questions. Do we have...
Working. So how does this tie into secure world? Like on ARM systems, there's a divide between normal world and secure world. And if you're describing the system, then it has to cover that part of the pond or whatever you want to call it. So what are the thoughts on that?
Yeah, so the idea, and of course this is a prototype, so there will be more thoughts. Every time we come with some ideas, talk to people, new things. So I'm not saying that this is fully baked, but we go back here. I'm bad at going back, turns out. So the idea here is that when you create these different domains, if you will, one domain might be the secure world. And you can actually use this in a hierarchical way, so that you could, for example, if you have a simple example where the secure world sees everything, and then you have your regular world, non-secure, that sees some part of that. Then you could specify that some part of that in one of these, and then you could specify the rest of the stuff plus include this one. So by doing this sort of hierarchically, you can group things together that belong together. And this tool, as we mentioned, is really a stupid tool that just goes into one of these, and then it traverses the tree, grabs the stuff necessary. And if you have some special things you need to put in there, for example, we have for remote proc for OpenAMP, then you can have a Python plugin that takes care of that stuff so that you get whatever tree that you need. Right?
Okay. Yeah, I was just wondering that would there be a sequencing thing as well, that this entire process first runs in the secure world, because there could be further partitioning in the secure world as well, especially now that we have virtualization, and the direction of travel is to divide things into secure partitions, which is kind of similar to what we are doing over here. So it's like the secure world has a go first, then it communicates to the normal world what it has done, and the normal world takes over and then kind of carries on with the rest of the process, something on those lines.
Yeah, exactly. So that's an interesting point. So right now, most of the creation of device trees sort of happening on the host, is what we're saying, and then you just get whatever device tree you're used to for, ATF or what have you, and you make sure that the tool can create that. As you go forward, you want to have more dynamic things and send things to. That's when all that comes in. That all right, you have to make sure that you have that root of trust and all that stuff. Absolutely.
Okay. Yeah, I guess those would be interesting discussions in the future.
Yeah, exactly.
Just one more thing. So we are looking at describing SMMU topologies and those kind of system architecture aspects as well. And that would be a standardized format. That's the intent over here.
Yeah. No, SMUs provide another sort of layer of interesting
Yeah.
stuff for this. I don't know how much we've done it. Will some thinking about it?
So my thinking is that, so we do definitely need to discuss this further, but SMMUs similar to interrupt controllers, so you can have multiple ones. For instance, the R5 cluster is going to have a different interrupt controller from the A53 cluster, and then you can use the extended interrupt properties that exist already to be able to point to the right interrupt controller, and then the Lopper tool will be able to narrow down the system divide tree to only the setting for related to interrupt relevant to your domain, which will be a subset of all the information about interrupts. And the same will be for the SMUs.
Yeah. And then there are further things like stream IDs and what context they map to, so it's going to be quite interesting.
No, definitely lots of interesting stuff coming up here. Last question before we... No one wants to go last. That's great. So we will have lots more of this on Thursday at 9 o'clock. And the room was, what did I say? Was it Bayfront or Bayview or something like that? Bayview, thank you. So everyone is welcome there, of course, and they will go much more deeper into examples and make sure that we get as much feedback as possible. All right, thanks everyone.